Hey guys, what's up? Welcome back to the classroom. It's Mr. Low, and today we'll be going through chapter 5, Turning Effect of Forces. Right, so you probably will have learned in lower secondary science that a force doesn't just change the motion of objects, but rather it also can cause some form of rotation, right? So we are going to explore that further in this topic and look at how we do this kind of calculations for rotation, right? So let's begin. Right, so the first part, right? When we talk about rotation due to a force, the name is called moments, right? So when we say moments, okay, we actually means it is a form of rotation, and let's look at the definition closely, which you should commit to memory word for word. Okay, so the moment is defined as the product of the force that caused that rotation, right? The product of the force and the perpendicular distance from the pivot, right? So a few things to take note over here. Okay, number one, of course, you need a force in order to create a rotation or moment. Secondly, the distance that you multiply the force to is not any other distance but the perpendicular distance from the pivot, which means you have to first identify in any problems about rotation where is the pivot. Okay, so let me start off with this very simple example over here. You have a rod and it is placed on a pivot over here. Okay, you have a force F acting upwards, and the force is at a perpendicular distance away from the pivot. So the moment created by this force, it's a product of the force itself and the perpendicular distance. Okay, so we'll see more complicated examples later, but for now this is it. The SI unit is for moment is Newton meters. So why Newton meters? Because force is measured in this Newton is for the force. All forces are measured in newtons, and the meters is because of the perpendicular distance. Right, so when you multiply force by perpendicular distance, you get the SI unit of Newton multiplied by meters. So Newton meter. Yeah. So let's label a little bit. This is the force that causes the rotation, and this is the perpendicular distance. Okay, so it's a very simple formula, but I just want to emphasize that we have to necessitate this perpendicular. This symbol here represents perpendicular. You can choose to write it like this, like you have learned in mathematics, because 90 degrees, right? You use a square to represent a 90-degree angle, right? So you have to do that because later on in the next chapter, when we talk about work done, you will see that the formula is very similar, but instead of perpendicular, it's parallel, right? So we will see more of that later on, but just bear in mind to write the symbol perpendicular in this case, right? So let's look at some simple and a bit more complicated examples. Okay, so first up, you have this. This is the most basic one, right? So you identify the force over here as 10 newtons, and of course the perpendicular distance to be 2 meters. So the moment, you just multiply the two numbers and you get 20 newton meters. So one thing to take note of, because moments is directional, that means depending on where the direction of the force exerted, the moment could be either clockwise or anti-clockwise. So in this case, how do we know whether it's clockwise or anti-clockwise? You can visualize, right, how the force will cause the rod to rotate. So since the force is going upwards, you can imagine that the rod is going to rotate in this direction. Hence, this is anti-clockwise. If you cannot remember in which direction is clockwise or anti-clockwise, just look up at an analog clock in your room or in a classroom. Then you can kind of tell from 12 to 1 to 2 that is clockwise, 12 to 11 to 10 that is anti-clockwise. Yeah, so this one is very basic things. Okay, next up, so this is when directional changes in the force may cause changes in the direction of the moment, right? So here we are still going to use the same formula. Moment equals to force multiplied by the perpendicular distance. It is still the same thing. It is still 10 newtons multiplied by 2, which still gives you 20 newton meters. So in this case, the magnitude is the same as before, But now the difference now here is that the direction will change, of course. So over here, the moment is going in the clockwise direction, right? Because the force is pointed downwards. So you have to indicate that the direction is clockwise. So in physics, we are very lazy. So we use short form to represent certain words. So we can use CW or ACW to represent clockwise or anti-clockwise. So you can use that in exams. It's understood. Okay, next up we look at two examples whereby it is not so obvious. So I'm going to teach you how to identify the perpendicular distance in this case if the force is not acting perpendicular to the rod in this case. So you can see that in the previous two examples, the force is actually perpendicular to the rod itself, right? Perpendicular to the rod. But in the next two examples, you will see that it's not so. You can see that the force is acting at an angle to the rod itself. So the way to go about doing this is we have to identify the correct perpendicular distance. So how do we do that? Right. So first, number one, when a force is acting in this direction, what we want to do is to extend the line using dotted lines. Okay, so we extend the line of force using dotted lines, like as I've written in green. Okay, so the next thing then is from this line of force, this green color line or dotted line, we want to find another line that from this line of force towards the pivot that is perpendicular to the line of force. That means in this case, we're looking for a line that is perpendicular to the green color dotted line and it extends towards the pivot. So if you're sharp enough, you realize that, okay, this is the line that I'm talking about, the blue color line. It is perpendicular to the green color line and it stretches from the green color line towards the pivot in this case. So identifying the pivot is critical in any situation. So first thing, you must go and identify the pivot. Right, so now we have identified that the perpendicular distance in this scenario is 4 meters. So once we have identified that, everything else is the same as before. The moment you just to find the moment, you multiply the force, right? The force, which is in this case 8 newtons, by the perpendicular distance, which is 4 meters, which we have identified earlier. Okay, and so how do we tell in this case whether is it clockwise or anti-clockwise? Very simple. Again, you visualize how the rod is going to rotate, right? So with the force going in this way, you can imagine that, okay, the rod is going to rotate in this way. So it's going to be clockwise. All right, so we look at another example that's not so obvious as well. Right now, the force is going in this direction. Okay, first we have to identify where is the pivot, right? So we see that the pivot is here. We label it for our reference. We see that, okay, we have a force of 8 newtons acting in this direction. So the next thing we have to do is identify the perpendicular distance to the pivot. So we extend the green color line, the line of force with dotted lines, and we locate a line that is perpendicular to it and extends to the pivot. In this case, this blue color one. Okay, so those who are strong in mathematics, you'll probably be thinking about, oh, I see Pythagoras theorem in this case, 3, 4, 5, right? This is a classic Pythagorean triangle. Yes, you can do that. You might want to do that to identify the different lengths, but I think in exams, we would not demand you to use Pythagoras theorem. If there is any length required, we should provide to you, okay? Because Pythagoras theorem is not in the physics syllabus, even though you know that knowledge. So let's move on from here. The moment, as usual, it is force multiplied by the perpendicular distance. We should have identified the force to be 8 newtons and the perpendicular distance to be 12 meters, and that gives us 96 Newton meters. And not forgetting the direction. In this case, it's acting to the left of the pivot. The force is acting to the left of the pivot and it's going downwards. So you can imagine it's going in the anti-clockwise direction as indicated by my black color arrow. right? So we can write down anti-clockwise ACW. It's understood. Okay, so yeah, in these two examples, we have seen how we can use the formula and to calculate moment. And of course, in the second case, how to identify the correct perpendicular distance if the force is not acting perpendicular to the rod, like this case, right? So how is it played out in real life, right? So if we push a door, we are actually causing a rotation about these door hinges, right? So the door does turn about this hinges, so it is also a rotation, it is also a moment. Okay, so as usual, we like to look at the question and identify the key information. So let's read through. Alice tries to open a door by pulling the doorknob at a distance of 1.2 meters, which you label as the D, away from the door hinge. She pulls with a force of 4 newtons, and you see that this is the force. So calculate the moment. This is the okay, I wouldn't use the word the symbol M, because M is for mass. So please spell out in full the word moment. Okay, so there's yeah, for us there is no symbol to represent moment, not at this level, so let's not worry about that. Okay, in this case, the next question actually you should ask yourself is this 1.2 meters the perpendicular distance? Answer is yes in this case. Why is that so? Okay, let me just quickly draw a door and using a rectangle, and the door hinge I'll represent using a triangle, which actually is the pivot in this case, right? So when you are pulling onto the doorknob over here with a force, yeah, it is indeed perpendicular to the pivot. So we can safely use 1.2 meters as the perpendicular distance. So the usual formula applies: force times perpendicular distance, and you get the moment 4.8 Newton meters. In this case, we cannot tell the direction, is it clockwise or anti-clockwise, because it depends on where you view it from. If you view it from the top view, like I drawn here, then yes, it is clockwise. But can you imagine if you view it from the bottom of the door, it actually looks like anti-clockwise. So in this case, never mind, we will ignore the direction for now. Okay, so next example, bicep curl. So common exercise in the gym, right? So first thing again you must do is to identify the pivot. So for those who did not perform this exercise before, you can imagine that, okay, there is a force acting upwards to lift the heavy dumbbell, and then how does the forearm, in this case, how does this forearm over here rotate? It rotates upwards, right? Okay, in this direction. I should use a black color arrow instead. So when you lift the dumbbell, the forearm and the dumbbell rotates upwards in this direction. So clearly the pivot is going to be at the elbow, right? So you can try to perform this task on your own with a water bottle or something, and you can see that, okay, the pivot is the elbow in this case, right? So you have the pivot, and then you also can find the perpendicular distance, which is 40 cm. Right? So the force needed in this case, of course, would be the force needed to lift the dumbbell lah. Okay, so let's analyze the question carefully. Right, so this fella is doing a bicep curl with a dumbbell of mass 15 kg. So notice that this is mass. Okay, it's not a force, but by experience you should realize that, okay, I can multiply mass by G to get a weight of the dumbbell, which should equate to the force that I need to lift it up. Okay, so the weight of the dumbbell in this case would be the force required to lift it up. Yeah, so we can calculate the force later on. Okay, and the forearm is about 40 cm, so that would give us the perpendicular distance. So this is your perpendicular distance, but there's a trick over here before we continue. Notice that the unit is given in cm, so we have to do some conversion later. Okay, so find the moments in this case. Yep, right, so we have to first write down the formula as usual. Moment equals to force multiplied by the perpendicular distance, and in this special case, the force required is the weight of the dumbbell. So I use W to represent it, multiply by the perpendicular distance. Okay, so now I need these two things, right? And I have to calculate them separately. So let's do the weight first. Okay, so the weight of the dumbbell, W equals to mg. This is from the previous chapter, right? And yeah, so we take the mass, which is 15 kg, multiplied by 10, which is the gravitational field strength on Earth, assuming that he's doing it on Earth, of course. So you have the weight of the dumbbell to be 150 newtons. Next, we go ahead and calculate the perpendicular distance. Remember, we have to convert because this is in cm, right? So we label that the perpendicular distance is 40 cm, which is also 0.4 meters. All right, so we have the two ingredients now. We can go ahead and multiply and plug into the formula. So now we have the moment. You take the 150 multiplied by the 0.4, and that gives us 60. Now in my answer here, I wrote ACW because I'm looking from this perspective, from this angle. But you can also imagine that if I'm looking from behind, right? So behind the arm, it will look like a clockwise motion. Try to visualize it yourself, right? So I shall ignore the direction for now because it's not very clear. But yeah. Okay, let's move on from here. Okay, last example here. Okay, this is a very classic test question, right? So let's try. Okay, so you have this bench. Now this is it can be made of rocks or wood, whatever. So it's a bench that is held up against the wall by a wire. Okay, so the question asks, what is the moment created by the wire? So there must be a force and there must be a perpendicular distance over here, right? So in this case, let's look at the wire itself. Okay, it has to support the weight of the bench, and the force in the wire over here is the tension. So here we have identified the force. We have identified the force over here to be the tension. Okay, now the next thing we need to identify before that, where is the pivot? That is the first thing we should identify. Right, you can imagine the weight of the bench, it is going to cause a rotation of this about the wall, right? And the wire is supposed to create a anti-clockwise moment to counter this moment. The pivot has to be over here. Okay, so this is the pivot. Okay, of which then the moment due to the wire is gonna be acted about. Right, so let me remove the weight first to avoid any kind of confusion. Okay, so you have the pivot, you have the force, and the next job, of course, is to find the perpendicular distance. Right, so you have 1 meters here, you have square root 2 over here. So this is when Pythagoras theorem will come in, because you would identify the perpendicular distance to be this one. This is the perpendicular distance. Okay, so how do I know that? Again, as usual, I locate the green color, the force with a green color arrow. I extend my line of force with dotted lines. Then I identify the blue color line to be perpendicular to it and extends to the pivot. So that is the perpendicular distance that I need to find out. Okay, and in this case, we will use Pythagoras theorem, even though it's not really in the syllabus, but just go with it. Okay, so as usual, we highlight the question first. We have the tension to be 45 newtons. So it's actually given. So this is the force, okay, and we need to find the perpendicular distance. So first, let's write down the formula. Moment equals to force multiplied by the perpendicular distance. And we have the force to be 45 newtons. So the next thing we need to find is the perpendicular distance. So let's stare hard at this triangle over here. You have a right angle triangle. Sorry, I should use pen. So you have a right angle triangle here in yellow, and we have square root 2 and 1 meter as square root 2. This is the hypotenuse, right? This is the hypotenuse. 1 meter is one of the sides. So, sorry, HYP, hypotenuse. Alright, so we have to find the perpendicular distance using the Pythagoras theorem. So I will not enforce the presentation here, but by Pythagoras. So by Pythagoras' theorem, square root 2, the square of the hypotenuse, is equals to 1 meter. I square it and I sum it up with the square of the perpendicular distance. Okay, so I can go and find perpendicular distance. Square of square root 2 is just 2. 1 square is just 1 plus perpendicular distance square. And we see that the square of the perpendicular distance is 1 meter, and therefore the perpendicular distance is just 1 meters. Of course, just a reminder for mathematics sake, when you take square root yourself on both sides, you should include plus minus. But in this case, we will reject the negative because we're looking at the distance, we're looking at the length. It doesn't make sense to have a negative length, right? So we will ignore the negative for now. So now we have found the perpendicular distance, we can go ahead and plug it into the formula substitute. So now we have moment equals to the force, which in this case is 45 newtons, multiplied by 1 meters. Right, so that is 45 Newton meters. And from this perspective, let me erase everything in the diagram to help you to see. In this case, the tension, the force, which is the tension, pointing this way, is going to cause a moment in this direction. So that is anti-clockwise. So we write now 45 Newton meters ACW. I'm sorry, my answer is wrong. Is ACW. Roger? Right. So in this special case, we are looking at Pythagoras theorem, but usually we would not. Okay, just application of your mathematics. Alright, so in this part, we're going to look at what happens when there are more than one moment acting on the same object about the same pivot. Okay, so the main concept here is called principle of moments. So I give you all a very simple example. So let's say I have a plank and I have a pivot, right, placed below the plank. In this case, let's say I have two forces, F1 and F2, acting on it. Each of these forces will create their own moment, right? So when we do that, when we have this kind of situation, we can go ahead and find the net moment, the overall effect, in the same way as in the previous chapter. If I have two forces, F1 and F2, acting on the same object, you can calculate the net force or the resultant force, which is the overall effect of the two forces on the same object. In this case, we can look at the overall effect in terms of moments, right, due to two forces acting on the same object about the same pivot. Now this discover portion, I'll leave it up to you to try, right? But the overall, if you do it diligently, you will arrive at this conclusion, which is actually called the principle of moments. Okay, so let me just go through the principle itself, which you should memorize, by the way. Okay, so the principle says that when an object is in equilibrium, okay, so this equilibrium, it means two things. So I come to that later. Okay, the sum of clockwise moments about the same pivot is the same as the sum of anti-clockwise moments about the same pivot. Okay, so it's a bit long, but this whole part can be summed up to this formula here, which is the clockwise moment equals to clockwise moment for an object to be in equilibrium. So in equilibrium also means that there is no rotation. Okay, so if I have no net moment, in this case, like the clockwise moment equals to the anti-clockwise moment, you can see that they sort of cancel out each other, right? So the object will not be rotating. Now this keyword equilibrium here, just to take note, there are two parts to it. One is called force equilibrium. Okay, so this for an object to be in perfect equilibrium, two conditions must be fulfilled. Okay, so one is called force equilibrium. This just means that net force equals to 0. So this is found in the previous chapter when we talk about Newton's first law. Okay, so when the net force acting on an object is 0, you get force equilibrium. So object will stay at rest if it was at rest, or if it was moving in a direction, it will continue to move at the same speed in the same direction. Newton's first law. In this chapter, we look at rotation equilibrium. Okay, so in this case, we're looking at rotation equilibrium. This just means the clockwise moment is equal to the anti-clockwise moment. And we're looking at the sum of the clockwise moments and the sum of the anti-clockwise moments. So that means if there are more than one clockwise moment, you have to add them up. If there are more than one anti-clockwise moments, you have to add them up as well. So we'll see some examples like this. Okay, but so the principle of moment just tells us that if an object is not moving, not rotating, then we can conclude that, okay, for about a particular pivot, the clockwise moment must be the same as the anti-clockwise moment, so they kind of cancel out each other. Okay, so a basic question here. We have this plank and we have the pivot here, and we have two forces, 5 newtons and unknown F. The question asks for what is the value of the unknown F if the object is in equilibrium. So in equilibrium, we know that, so this is something that I need you to write down. By the principle of moments, sorry, wrong tool. By the principle of moments, this is something that you need to write down. We see that, okay, if the object is in equilibrium, then the CW moment must be equal to the ACW moment. Yeah, so in this case, there is only one CW moment and one ACW moment. So the CW moment is this guy, and you have one ACW. So these two moments must be equal to each other for the plank here to be equilibrium. Yeah, so we can immediately write down the formula. ACW moment equals to, we calculate to be 0.5 F. In this case, the distance is given in cm, so we have to convert it to meters. Yeah, so again, it's the same thing, right? The moment is force times perpendicular distance, of which for this simple case, the distance is perpendicular distance is 0.5 meters, 50 cm. So that is the ACW moment. Okay, so for the CW moment, we have again the same thing, force multiplied by perpendicular distance, and we get 1.5 Newton meters. So this 1.5 Newton meter should be equal to this 0.5 times the unknown force. So from there, you can go and back calculate the force to be 3.0 newtons. Okay, so in this case, we only have one clockwise and one anti-clockwise moment about the same pivot, but in the principle itself, it says look at the sum of the two moments. Okay, so this is shown in this kind of example where you have for the same pivot, right? There's more than one clockwise and moments and more than one anti-clockwise moment. So first, again, as usual, identify the pivot, and then next thing is we want to identify who are the clockwise moments and who are the anti-clockwise moments. So we can see that, okay, for clockwise moments, we have these two guys here, and then for anti-clockwise, we have these two guys. So when there are more than one clockwise and more than one anti-clockwise, we have to sum them up. Okay, so part A, the question kind of breaks down for you what is the sum of the CW moments. Okay, so we can do this together. For part A, we look at the two CW moments here. So we must be careful with the perpendicular distances when you calculate all this. Okay, so CW moments. In this case, I have two players at play. One is this 10 newtons multiplied by 0.6. So we have the first one, 10 multiplied by 0.6 meters. And then you add on to the second one. Now the second one is a little bit tricky, right? Please don't get fooled. It's not 5 times 0.4, but rather is 5 times 1 meter, because the perpendicular distance is this whole guy, right? This whole stretch over here from the force to the pivot itself, that's 1 meters altogether. So you can take 5 and you multiply by the sum of the two lengths. That gives you 6 plus 5, and that gives you 10 times 0.6, 6 plus 5. Okay, so that gives you 11 Newton meters. So my bad, these two answers should switch. The clockwise and anti-clockwise moments are opposite of each other. Okay, my bad. So let's move on from here. Now we look at the two anti-clockwise moment, ACW. Okay, so now we have two players here, 2 newtons and 8 newtons. So I take the first one, 2 times 0.5. I add on to the second one, which is 8 multiplied by the sum of the two distances. In this case is 0.5 and 0.5. You get 1 plus 8. That gives you 9 Newton meters. Okay, so we see that, my apologies, sum of. Okay, so we're looking at adding the two together. So we have the sum of clockwise and anti-clockwise moments. The next question asks for the net moment, which is the overall effect. Okay, so we can go and calculate. So the net moment. So we take the biggest number minus the smaller number, yeah. So 11 minus 9, and that gives us 2 Newton meter. Now this is when the direction matters, right? So the bigger one will dominate. In this case, the bigger one is the clockwise moment. Okay, so the bigger one is the clockwise moment. So the overall effect or the net moment is in the clockwise direction. So part D asks, is the beam balanced? Answer is no, of course not. Okay, and of course you can go on and explain, saying that the net moment is not 0. So in this case, we do not have equilibrium. I say again, we do not have equilibrium. In the previous question, the plank is in equilibrium because the clockwise moment equals to anti-clockwise moment. But in this case, the clockwise moments dominate. So you can imagine that the plank will now rotate, okay, in the clockwise direction. So if not, then how would it turn? Of course, in the clockwise direction. Alright, next up we look at the next example. Okay, so let's go dive right into it. So you have Sam and his parents are seated on a seesaw. If the seesaw is in equilibrium, so this is when a second example whereby the net moment equals to 0. Right? That also means that clockwise moments equals to anti-clockwise moments. So I just write it simply as net moments equals to 0. And the question asks for the value of x, knowing that all their weights are given. Okay, so we can first, again as usual, go and identify the pivot, okay, and then identify the clockwise moments and anti-clockwise moments. In this case, the father will produce the clockwise moment, or rather the weight of the father. In this case, the weight of the other two person will create the anti-clockwise moment about the same pivot. Okay, so in this case, they are in equilibrium, so we can conclude that these two will be equal in terms of magnitude, in terms of the size. Yeah. Okay, so we can go ahead and calculate the clockwise moment first. Okay, so clockwise moment. So this is equal to, we take the force multiplied by the perpendicular distance. In this case, the force is the weight of the father, so it's 700 multiplied by perpendicular distance of 2 meters. That gives you 1004 Newton meter. So we keep that in view first because later this number will be equal to the ACW moment. Yeah. Okay, so now we compute the ACW moment, bearing in mind that the unknown x. Yeah. So in this case, since there are more than one, we have to write the sum of anti-clockwise moments. Okay, so we go and calculate first. First we have Sam, that is, who is 400 newtons. We multiply it by the distance of 2.0, and you add on the moment created by the mum, which is 600 multiplied by the big X, the distance X. Yeah, so this is 800 plus 600x. Okay, so we do not know the value of x, so we keep it as it is. So since this object is in equilibrium, this is when you need to write down by for your presentation purposes, write down the line by principle of moments. Okay, by principle of moments, it says that the object is the plank, the seesaw is in equilibrium. Therefore, the CW moment equals to the sum. In this case, there are more than one. The sum of ACW moments. Okay, so we can equate the two expressions together. So I'm going to put the ACW on the left hand side for ease of calculation. So 800 plus 600x equals to the moment that the father created. Okay, so now you have a basic algebra 1 unknown equation. So the usual way to go about doing it is you shift the 800 over to the other side, minus, and then you divide it by 600. Okay, so in this case, 1004 minus 800 happens to be 600. So it is 1.0 meters. And there you have it, right? The mother is seated 1.0 meters away from the pivot of the seesaw. Great. All right, so we are done with principle of moments, and we move on to the sort of the last concept over here in this chapter, which is called CG, center of gravity and stability. So you've probably heard of the word center of gravity, but what does it actually mean, you see? Okay, there's a lot of misconception over here in regards to this concept, so let's be sharp about it in our thinking. Okay, so first of all, CG, center of gravity, is not a mass quantity, neither is it a weight quantity. So many people see the word gravity, they think of it like a weight kind of a thing, gravitational force. They perceive CG as a force, but actually no, center of gravity is a point. It's not a force, not a mass, but actually it's a point in the object, or sometimes it's outside of the object. Okay, what is so special about the point is that this point is almost as if the whole weight of the object appears to act on. Okay, what do I mean by that? So let's use this object as an example. So let's say I have a rectangular card. Well, a rectangular card is an extended object in the sense that you can break it down into many parts. Let's say this part of the card itself has its own weight. This part itself has its own weight. I call it weight 1, weight 2, so on and so forth, right? So if I cut the cut into small pieces, each of these little pieces have their own has its own weight, you see. So if I want to then decide on to express the weight of the whole card, of course, it's just a sum of all the individual pieces, the weight of the individual pieces. But if I were to choose a particular location whereby the object, the weight is acting, the gravity force is acting on the object, then I would choose the point called the CG, right? So the CG, center of gravity, is just a point whereby I assume all the gravitational force acting on the object is acted on. So it's not acting on this location, neither is it this location, but the CG of the object, the center of gravity of the object. Okay, so for a symmetrical object, I think it's quite clear. For rectangular, square, circle is always at the center. Triangle also at the center if it's a perfect triangle. Yeah, for a circle like this. But for certain weird shapes of figures, the CG does not lie on the object itself. So you see, in this case, it's a ring. The CG is outside of the ring. It does not fall within any part of the ring itself, right? So So in this case, we are not really expected to know for every shape where is the CG, but there is a particular way to find out experimentally. Okay, we may do it when we come back to school. Okay, so why are we talking about this, right? Because in the previous examples that we dealt with, all the horizontal planks, or the seesaw in this case, we did not take into consideration its own weight, you see. Right, planks and seesaw like this, we know that they have weight, they have their own weight, of which is also a force. So that means if we take into account the weight of the plank itself, then we may end up with another force and another moment to deal with. Okay, so let's look at two simple examples. In this case, if I take the plank to be a uniform, that means equal thickness and same materials throughout, then I can safely assume that the CG is right smack at the center. Now, if the pivot is placed directly below the center of gravity, first thing you know that the ruler or the plank itself will balance. That's common sense. Now the next question is then, since I'm now considering an additional force, which is the weight of the plank itself, what is the moment generated by this weight of the plank itself? Yeah, so in this case, the moment here, if the pivot is directly below the CG itself, then common sense would tell you that actually there's no moment generated, because the overall result is that the plank is not rotating, so there's no net moment in this case. So why is that so? Why is that the weight does not generate any moment? It is because the perpendicular distance is 0. So moment, as we know, is force times the perpendicular distance. Now in this case, the force we are talking about here is the weight of the ruler or the plank itself, and the perpendicular distance in this case happened to be 0 because, well, the pivot is directly below the center of gravity. So in this case, the moment generated by this weight is 0 Newton meters. It's 0, which is good news because we do not have to consider the moment due to the weight itself. So we don't care, right? So anything that we just add on, let's say I add on another weight over here, I just consider its moment. So I don't have to care about the moment due to the weight. But however, if we are to place the pivot away from the CG, then you have a problem, because now there is a moment generated by the weight of the plank itself, which we have to take into consideration. So in this case, if I place the pivot at 20 cm mark, right, now there is a perpendicular distance from the pivot to the weight itself, and that is 30 cm or 0.3 meters. Remember, we have to work in SI units most of the time. Okay, so the moment due to the weight of the plank itself, now we take the force multiplied by perpendicular distance. The force is the weight this time round, and sorry, not equal, and you multiply it by the perpendicular distance, which is 0.3 now. So this is 0.3 times the weight, Newton meters. Of course, we don't know. Oh, we know the weight. Sorry. Okay, because we have the mass of the plank. Okay, so let me just do the calculations here. So now the weight is, we take W equals mg, right? So we are W is equal to mg. So we multiply 0.1 by the value of g, which is 10. In this case, it's a nice 1.0. So the moment is simply 0.3 Newton meter. Well, the number doesn't quite matter, but what matters now is that the moment due to the weight is no longer 0. So I have another moment to take care of. Yeah. Okay, let's move on from here. Okay, we look at this particular example. So now, in this case, we have 3 forces, 2 Newton, 4 Newton, and unknown F. The question says that the upward force, this F, is needed to keep the beam horizontal, which actually means to keep the beam in equilibrium. To keep it in equilibrium, right? So again, this also means that net moment equals to 0 lah. Okay, because equilibrium, yeah. Okay, so first up, as usual, we have to identify the pivot. Okay, in this case, you don't see a triangle being placed below the horizontal bar, a beam, but you have this little circle here. So this is where the pivot is. Okay, so everything has to, not pi, it's a pivot. So everything has to take reference, all length has to take reference to this, the location of the pivot. Yeah, so since it's in equilibrium, so again, by principle of moments, I have to quote this down. Okay, CW equals to ACW moment. Okay, we look at the clockwise moments first, which is due to these two fella. Clockwise moment and the unknown force F generates an ACW moment. Right, so we sum out the two moments. Actually, it's a sum of CW moment, and we get 1.0, and then for the ACW moment is force multiplied by the perpendicular distance of 0.4 meters. Right, so 0.4 F. So by principle of moments, these two numbers equate. 1.0 equals to 0.4 F. We get force equals to 2.5 newtons. Right, so this is how it can play out. Now in this example, of course, the significance of this 4 newtons is because the beam itself has its own weight, right? So this is the weight of the beam itself. So in exam questions, we may not give you the diagram, so you have to take note, when do I have to consider the weight of the plank itself, or the horizontal beam, when it comes to calculating moments. Yeah. All right, now we come to the next example over here. Okay, so here we have a wheelbarrow. This wheelbarrow will be lifted by this force over here, and the question asks for the minimum force required to lift this wheelbarrow. Okay, so the way to go about doing this is, it's not that the force is lifting the entire wheelbarrow up, but rather it is causing a anti-clockwise moment about this particular pivot over here. Okay, so this anti-clockwise moment should counter, or rather should be greater than the other two clockwise moments created by the two weights over here. Okay, so first we have to go back to the question and read again. The basket has a weight of 50 newtons, while the metal frame has weight of 120 newtons. So I have to use these two weights as forces to go and calculate the clockwise moments, and then later on the ACW moment should be greater than the 2CW moments. So this is the game plan, the strategy. Yeah, so let's go ahead and calculate the sum of CW moments. So in this case, I'm taking the weight of the basket and I multiply it by the distance, perpendicular distance. In this case, it's 50 cm, but written in meters, yeah, so 0.5 meters. And I'm adding on to the moment due to the metal frame itself, which is 0.5 plus 0.2 multiplied by the weight, 120. So this is 25 plus 120 multiplied by 0.7. So this is 25 plus 84. So I'm doing mental sum over here, so it's a bit slow, which gives me 109 Newton meters. So this is the sum of the anti-clockwise moments that I need to overcome with the force, the ACW moment. Okay, so in this case, a better way to represent this is that I know that in order to lift up the wheelbarrow, I'm no longer looking at equilibrium, right? But rather, the ACW moment must be greater than 109 Newton meters, because so that the whole wheelbarrow can tilt or rotate in the ACW direction. Okay, so first I go and calculate the ACW moment. And that is the force multiplied by the total perpendicular distance, 50 plus 20 plus 70. of course converted to meters, yeah. So this gives me 1.4 times force. Okay, so now it's your mathematics. Your 1.4 F must be greater than 109, which means the force must be greater than approximately 77.86 newtons. And they ask for the minimum force given to the nearest 1 newton. So therefore, my force, minimum force should be equals to 78 newtons. Okay, so if the force is exactly 77.86, it will not lift up the wheelbarrow because the moments are equal, you see, the clockwise moment equals to the anti-clockwise moment. You get an equilibrium, yeah? So you need something bigger than that. Okay, the last concept here in this chapter is called stability. So I don't know whether you have seen this kind of roly-poly toys. Basically, they're heavy at the base over here and light on the top. So the way to play this toy is that you exert a force to one side and causing it to tilt a little bit, just like this case over here. And then when you release it, you will actually rock left and right, and you will go back to the original position, the equilibrium position. So no matter how much you tilt, right, if the base is heavy enough, it will always return back to this equilibrium position. So this toy is said to be very stable. So what do we mean by stable, right? So again, another definition to memorize. Stability refers to the ability of the object to return to its original position after it has been tilted slightly. The keyword here is slightly. Of course, there are some objects not as stable as this. If you tilt enough, it will of course collapse. It will of course fall onto the side that you push it to. So the keyword here is slight tilting, right? So if the object can return back to the original position after it has been tilted slightly, then it is considered as stable. Now, for something to be stable, the main two concepts here is there are two ways you want to modify the object or design the object to make it stable. So one is the CG must be as low as possible. So if you look at this roly-poly toy, the design is such that the base is heavy. So when the base is heavy, the CG is no longer right smack at the center, but rather it has been shifted, you'll be shifted downwards to somewhere nearer to the base because the base is heavier. There's more mass distribution towards the base, right? So the CG is lower than if you did not, it will be lower than if you did not make the base heavier lah. So having a lower CG will make it more stable. Okay, so that's number one. Number two, the area of the base in contact with the ground must be as wide as possible. So I give you an example here. If I have a triangle toy and I put it like this on the floor, compared to if I just turn it around and place it like this, then clearly you will know that in the second case, it's more stable because the base is wide compared to this little pointy this apex over here. All right, so the way to make it stable, these are the two ways. Yeah, so we look at two examples to illustrate this concept. Okay, number one, which of the following arrangement will result in the most stable configuration and why? So in this case, I think common sense, I think it's quite easy for all of us, but just to illustrate a little bit more is that the bases are the same, you see. So you're looking at the same base contact area. So we are no longer playing with that, but rather we're playing with the mass distribution of the books on the shelf. So you want the CG to be as low as possible. Looking at point number one, you want the CG to be as low as possible. Therefore, option B is the best, and option D, of course, is the worst. Okay, so configuration B is the best, and why? Its center of gravity is the lowest. So this makes, let me just rewrite it again. The center of gravity is the lowest. Okay, so this makes the shelf most stable just by lowering the CG itself. Okay, so this makes the shelf more stable. All right, so now we are looking at the CG, right? The position of the CG itself. Okay, next we look at the another example that plays with both CG and the base area. Okay, so here we have F1 car and the usual salon car, the usual car that you sit in. This question gives the maximum height, which kind of suggests for us the position of the CG as well, and also the base dimension. So this is the base area, right? So F1 is designed to be very stable, so it can navigate tight turns without flipping at high speeds. So how does this design make F1 a very stable vehicle compared to the usual salon car? So here, of course, you have two factors over here, which utilizes both the concepts, right, of low CG and white base. Okay, so how does it? So number one is that the center of gravity, I'm gonna use shorthand CG over here. Okay, the CG, please spell in full in exam. The CG of the F1 car is lower than the salon car. Next is the base area. The F1 car. In this case, you can actually do a bit of mathematics, right? So you can see that this is actually not 18, this is 1.8, sorry. Okay, so you can see that, okay, 4.6 and 4.41, in exam you might want to press the calculator and provide the numbers, but otherwise it's fine as well. So the base area of the F1 car is larger than the base of the salon car. So here we have two factors making the F1 car more stable than the salon car itself. Okay, so 2 pointers here. Great, and so that's it for this chapter. Just do a quick sum up. So in this chapter, we learned about the rotation effect of force, which is also known as moments. We have the base formula, moments equals to force times perpendicular distance. We look at how we can find the perpendicular distance in weird situations whereby the force is not perpendicular to the pivot. And then we look at the principle of moments that says that if an object is in equilibrium, that means no rotation, then we know that the sum of CW moments must be equals to the sum of the ACW moments, which we can apply in different situations to do calculations. And then we look at the idea of CG as a point, not as a weight or as a mass, but it is a point of which the whole weight, the gravitational force appear to act on the object as a whole. Okay, so the reason for pointing it out is because if the pivot is not at the CG of the plank or the horizontal bar, then we have to take into consideration the moment generated by the weight itself. Yeah, so we apply that into situations. And last but not least, we look at the idea of stability, which is the ability of the object to return to its original equilibrium position after being tilted slightly. Yeah, so there are two factors here. One is low CG and the second one is white base area. So with that, I hope you understood this chapter broadly, and I'll see you back in class. Take care.